Good afternoon to everyone. I first would like to introduce myself. So I'm Carolina Mora Lopez. I have been involved in the development of Neuropixels projects from the beginning. Normally, I'm invited to this course to give a little bit of overview about the technology. So it will be really from the engineering side. I hope it won't be too heavy. But the idea is to give you an overview of how the probes are fabricated, what are the new developments, and this specific year I was requested to talk about the new Neuropixels NXT or 3.0. Maybe just to clarify the question of Mateo, what's the name? So Neuropixels NXT is the original project where we started the first development of this technology, but eventually when we further mature the technology and we are ready to release it to the public, this will become Neuropixels 3. So at this moment, we still call it internally NXT just because it's like the first part of the development. Good. So I will start maybe by introducing Imec. So I'm working in Imec. This is a research organization that is located in Belgium. What is special about Imec? We are a center in research and development on nanoelectronics and digital technology. It's a very large institute. We have more than 6,000 researchers and talents from a very international background. What makes Imec special is the infrastructure. So we have leading edge semiconductor fabs here in Europe, which are very important to design, fabricate, manufacture all parts of technologies related to silicon technologies, scaling for many types of applications. So my work specifically and the work of my team here that is actually designing both the probe and the system for Neuropixels is in the health sector. So we are specialized on biomedical circuit design and system design using this infrastructure that we have at Imec. What does it mean for Neuropixels? Then we have specialized materials like the electrodes that are very low impedance, biocompatible, and very uniform. Also the probe fabrication that has all the, let's say, the MEMS part of the process. To fabricate and later package all this technology that we put at your hands. As mentioned, Imec is in Belgium, but right now we are doing a little bit of an expansion in the US, in Europe as well, to try to capture a lot of talent at the moment to be able to develop very advanced technologies in silicon. We need a specialized talent that is not always available in Belgium. So Imec has been trying to capture those talents by probing local expertises in different countries. And I told a little bit about the work at Imec, specifically for health. We actually cover many applications from DNA sequencing, things for analytics, electrochemical sensing, cell culture, so technologies also for in vitro platforms. And of course, our main activities now are on the neural probe technology and developing then all the generations of Neuropixels also for the future. Maybe for the people that doesn't know what Neuropixels is actually an electrophysiology tool that was developed in order to miniaturize and to scale up all the electrophysiology readout experiments. So what we target from the beginning of the project was to integrate in a single miniature device that is made out of silicon all the electrophysiology equipment that you normally use in your animal experiments. This will increase not only the signal quality because the electronics is much closer to the electrodes, but also the throughput of those experiments. So you can get much more data on a single experiment. these probes are fabricated out of silicon. Here I'm showing some of the pictures of Neuropixels 1, specifically for Neuropixels 1 and Neuropixels 2. We were using 130 nanometer technology that give us a very good performance in terms of the noise requirements and other properties that are important for this type of low frequency applications. What happens then with the probes is that after we do CMOS processing to fabricate the circuits, all the electronics that is inside the probe, this comes then to our Imec fabs in order to fabricate the probe itself. So it's really the post-processing, we call it, to be able to do the probe shape, release the MEMS, that is a very thin silicon chunk, and to deposit also the electrodes. So we designed so far 2 probes, Neuropixels 1 at the left and Neuropixels 2 at the right, where we had at the moment quite a good performance, of course, in the level of functionality that we had. So one of the works that we did for Neuropixels 2 well, first, we wanted to have a 4-shank probe with many more electrodes, but much smaller. So we wanted to reduce the area of the probe significantly, while keeping the same performance in terms of noise, power consumption, and we achieved that. So we were very happy, I think, with this scaling down because we managed to keep this performance. But moving forward, our next task that we got assigned by the Neuropixels Consortium is, can we increase the number of channels by 4 times while still keeping the same area and the same performance? And unfortunately, the technology that we used for these probes was not longer good enough for that scaling. And that's why I put these red faces here, indicating that that technology, achieving the area and the power consumption were just, it was not sufficient. So what we did for a couple of years was, if you look at here, the readout, so this is really a screenshot of the electronics of how it's fabricated in this chip. If you look at Neuropixels 1 and 2, we did a great job scaling the area of the readout channel. And then what we did later was to start exploring technologies and architectures that would allow us to scale further. After this exploration that we did with several CMOS technologies and different type of readout architectures, then we come up with one that was mature enough to be able to go into the next challenge, what does Neuropixels 3, and then that started as a project funded by the NIH called Neuropixels NXT. So within Neuropixels NXT, and this is a little bit of overwhelming of a diagram, but the message I wanted to convey with it is that we completely redesigned fully the circuits that we had in Neuropixels 1 and 2, completely from scratch to develop then a probe that is fully optimized for a small area and low power. And including also some important blocks. One is on the power management, so that you don't need to have outside of the probe a lot of the regulators and power generation. So that is all on chip. We also have that in Neuropixels 2. And the other is also in a very optimized and low power digital protocol for the transfer of data that was ultra low power LVDS. And then we also had some internal blocks for the clock generation. So this was a very intense work in order to have then this new generation of the probe. And at the end, it's a very impressive result. So we managed to achieve really 4 times the number of channels into the same area as Neuropixels 2. So if you look at the probe shape, it's very much the same form factor of around 2/8. That's the same as Neuropixels 2. But with 4 times the number of channels and with the same performance, and I will show that in a moment. And also one of the efforts we wanted to do was also on the packaging side. So one of the things that we also changed in Neuropixels NXT is to make sure that the power management block didn't need external capacitors, so that also the system side was much smaller. And here, just a comparison, not need to go through all these numbers and table, but the message I wanted to bring here is that there are important parameters when you design this kind of tools that are the area, the power, and the noise. These things are in a trade-off from fundamental limits of the CMOS technology. There is always a trade-off between noise, area, noise, and power. And then the goal of the Neuropixels NXT, that is this green part here, was to really miniaturize all these parameters at the same time. And we achieved that. So now the performance of Neuropixels NXT, that will become Neuropixels 3, is then by giving the same noise as the previous versions, we actually have a much smaller device with more channels. So yeah, I think that's everything from my side. And here the final comparison then. I wanted to show here in the last part of the picture that we are also making some efforts on the miniaturization of the flex and packaging. We are not there yet with this, so we are still doing a lot of effort on that front. And once we solve all the challenges, then we will be able for the proper release. Thank you.